Good morning. So, in the last class, we were discussing the characteristic curve of PN junction. I will give a brief review of the characteristic curve of PN junction, and then we will see one of the devices where PN junction is used, or we can use the PN junction as as a rectifier, diode rectifier, and we will see how it functions. So a PN junction, when it is forward bias, it offers less resistance to flow of current. And you can see in this graph that the current in the forward bias is of the range milliamperes. And when it is in reverse bias, it is given in the range microampere. Micro means 10 raised to minus 6 amperes. So it's very less. And milliamperes is 10 raised to minus 3 ampere. So still it is small current and it can flow through the diode. Here you can see when we apply a forward voltage means when the diode is connected in the forward bias, then the positive terminal is connected to the p-type and negative terminal is connected to the n-type. And the current will flow in the direction of the arrow mark, that is from p to n. So in the beginning, there are not much current flowing. So if the potential applied is very small, there is no current flowing because there is a barrier to the flow of current. But when the potential applied is more than a particular value called the knee value, threshold value, or cut-in voltage, then what happens? The current steadily increases. So the current increases very quickly in the forward voltage, or we can say that the diode conducts after the cut-in voltage or after the threshold voltage. Now, when we look at the reverse connection, where in reverse bias, the positive terminal of the battery is connected to the n-type of the PN junction and the negative terminal of the battery is connected to the p-type. In such a case, initially there will be very slight flow of current. See, it's in the milliampere and it's still less. So nanoamperes may be very small. Current will flow. This flow is due to the minority charge carriers, and that current is called the reverse saturation current or the leakage current. It's just a leakage. It's not due to the majority charge carriers in the p-type region or the n-type region. But if we increase the reverse voltage, after a particular voltage, there is a breakdown. Breakdown means the PN junction no more functions like a normal PN junction. In a reverse voltage, all the donor atoms becomes ions and all the acceptor atoms become ions. All the donor atoms will lose their electrons, which they usually provide as a free charge carrier. They lose them and they becomes ions. And also all the acceptor atoms, impurity atoms, must have accepted an electron, and they are not providing holes. It's not available there, and they will be ions. So it is broke down completely, and that voltage at which it breaks down is called the breakdown voltage or Zener voltage, and the current is obtained. The current start flowing. The PN junction no longer will have its normal characteristic. So again, it's a current in the microampere region. So this is the characteristic of PN junction, and notable or measurable quantity here is the resistance. So let us see how we can calculate or find the resistance in the forward bias and the reverse bias. So it is usually called dynamic resistance. Dynamic means in the working condition. So what is dynamic resistance? It is the resistance offered by a diode in conducting electric current when an external voltage is applied. So when external voltage, either the forward or the reverse, can have a dynamic resistance. So let us see how we can calculate it. So you know that resistance is voltage by time. So dynamic resistance is the change in voltage by change in time. So you can just draw a triangle here, and this amount expressed in ampere will give you delta I, and this amount expressed in volt will give you delta V. So the resistance is delta V, that is this voltage range divided by this voltage range, sorry, this current range. So delta V by delta I can be calculated from the graph or the characteristic curve of a PN junction diode. In this figure, we have shown only the forward characteristic curve. You know there can be a reverse one as well. So the resistance offered by the diode to forward bias is called the forward resistance, and the resistance offered to reverse bias is called the reverse resistance. So the ratio of reverse resistance to forward resistance is shown here. See, for germanium, 40,000 is to 1. So for germanium, which is more, reverse resistance or forward resistance? Which is more?
Forward resistance.
Forward resistance is more. If
No,
forward,
the reverse resistance.
reverse resistance is more, because when forward resistance is 1 ohm, reverse resistance will be 40,000 ohms. So reverse resistance is much high, means if it is reverse bias, it cannot conduct electricity. Forward resistance is much less than the reverse bias, means in forward condition, it can conduct electricity. Okay. So what about silicon? The ratio of reverse resistance to forward resistance is 100,000 is to 1. So which is more, reverse resistance or forward resistance?
Reverse resistance.
Is more. So when it will conduct electricity, when will a silicon conductor conduct electricity, or a diode made of silicon by adding impurities conduct electricity? Which condition? Forward or reverse? It will conduct electricity when it is in forward, because the reverse resistance is very high, so it cannot conduct electricity. So for ideal resistors, you can see the difference in resistance. It's very high, right? When it is reverse, it is very high. So for an ideal PN junction diode, we assume that it conducts electricity without much resistance when it is forward bias, and it cannot conduct electricity when it is reverse bias. Now, let us see how this property of diode help us. So, due to this property of a diode, we can use it as a rectifier. What is a rectifier, or what is called rectification? The process of changing AC voltage into DC voltage is called rectification. So what is AC? What is AC?
Alternating current.
Yes. And what is DC? What is DC? You know, AC is alternating current. So what is DC? Direct current. Alternating current means a current which changes its direction. So if a current is going in this direction once, and uh, the current after a few moment or a fraction of a second, it will go in the opposite direction. Again in this direction, again in the opposite direction. So this is an AC current. See, up. This crest part or up part is called the positive half cycle, and this down part is called the negative half cycle. So in the up part or positive half cycle, current will be going in one direction, and in the negative half cycle, current will be going in the opposite direction. Again, it changes its direction. Usually, in the supply AC voltage, we have a frequency of 50 hertz, which means in 1 second it changes its direction 50 times. So in 1 second there will be 50 positive half cycles and 50 negative half cycles. So here you can see in this figure, this is AC. AC means alternating current. It changes its direction many times in 1 second. And DC means it will not change its direction. So this is an example for DC. So the current goes, there is only positive half cycle, but there is nothing in the negative half cycle, which means it's not going in the other direction. So it is an example for a DC. Rectification is the process of changing AC voltage to DC voltage. And rectifier is a device that converts AC to DC. Now let us see how a diode acts as a rectifier. Now if you use one single diode, it acts as a half wave rectifier. A half-wave rectifier is a type of rectifier that only allows one half cycle of the AC voltage waveform to pass, blocking the other half cycle. So here you can see a half-wave rectifier. Half-wave rectifier. What is this? Do you have any idea what is this? There is a primary coil, a secondary coil, there is a core. What is this symbol? You have learned about something which a primary with a primary coil and secondary coil. Do you remember what it is? It is called a transformer. So this is a transformer. Why do we use a transformer? For what? We use a transformer to step up or step down voltage, which means to change the voltage and current, we use a transformer. Usually the supply voltage is very high, about 220 volt. Now when you pass it through a transformer, here you can see the primary has more number of turns than the secondary. So this is a step down transformer. So when you apply a high voltage here, you will get a high AC voltage. If you apply here, you will get a low AC voltage. So the voltage is reduced using this transformer. Now, when you connect it to a diode, we know that this is P type and the dash is N type. So current can flow in the direction of the arrow mark and current cannot flow in a direction opposite to the arrow mark. Now let us consider during the positive half cycle. During the positive half cycle, this end, upper end becomes positive, lower end becomes negative. So current usually flows from the positive to negative, right? So current flows in this direction. That is in the direction of the arrow mark. So current will flow like this through the load resistance. What is load resistance? Load resistance can be any device which works on DC. For example, it can be a small radio, it can be a bulb, it can be a small motor, okay? So it can be any device which can work on DC. So that is a load resistance. So current flows through the load resistance during the positive half cycle and it gets completed here. So during the positive half cycle, when the upper part is positive, lower part is negative, current flows through the diode, load resistance, and the circuit is complete. So through the load resistance, we get an output. We get an output which is the positive half cycle. Now let us assume the negative half cycle. Negative half cycle means the current changes its direction. So up we have negative now and down we have positive. So the current will be going from positive to negative. So the current should flow from here to here, right? So when the current start flowing from here to here, when it reaches here, can it flow through the diode? Is it in the direction of the arrow mark? The current is going from here to here. Can it flow? Can it flow through the
Yes.
diode now? I need some response.
Teacher, can you repeat?
Yeah, during the negative half cycle, the direction of current changes. So up you have up you have negative and down you have positive. So the current is going from positive to negative. So it is flowing from here to here, it's coming here. Can the current pass through the diode? It's coming like this. Current is not flowing now along the blue arrow mark. It is coming in this opposite direction. Can it flow?
No.
No, because it is reverse bias, right? If the current is going along the arrow mark direction, it is forward bias. It can flow. Now, if it is flowing in the opposite direction, which means it is reverse bias, this is negative. So, it cannot flow. So, in the reverse bias condition, the diode will not conduct. So, if the current is coming opposite to the direction of the arrow mark of the diode, it cannot flow. Therefore, the negative half cycle will not flow through the load resistance and they are cut off. Okay, so only during the positive half cycles, the current will flow. During the negative half cycles, the current will not flow. So that is the condition for a half wave rectifier. A half wave rectifier is a type of rectifier that only allows one half cycle of an AC voltage to pass, blocking the other half cycle. So half wave rectifiers are used to convert AC to DC voltage and only require one single diode. So this is a half wave rectifier. Is this clear to you?
Yes.
Okay, so this is a half wave rectifier and it uses only one single diode. Now let us see what is a full wave rectifier. So a full wave rectifier, both half cycles of AC will be available in the output. And see, this is the input voltage we give. Input AC we give for a full wave rectifier. This is the output we receive in a full wave rectifier. See, both the positive half cycle and the negative half cycle appear but in the same direction. So this is alternating or it is changing its direction. The input is AC, but the output is DC because it is not changing direction. Of course, it is pulsating. Still, it's in the same direction. So this is a full wave rectifier. So what is a full wave rectifier? A full wave rectifier rectify both half cycles of AC. And for that, four diodes connected in the form of a bridge is used. So this is the circuit for a full wave rectifier. In your textbook, they have shown this load resistance here and it is connected to the other side like this, but it's same. I think this is a simpler circuit for you to draw. You must know how to draw the diagram for full wave rectifier. So you have to learn this diagram. Now tell me, what is this? What can you see here? What is this device?
Transformer.
Yeah,
Transformer.
this is a transformer. So you have the primary coils and the secondary coil. So from the AC supply, first you apply to a transformer. It should be a step down transformer. It's not clear from the figure. They have shown both the number of turns same, but it's just a symbol. So it should be a step down transformer, and then the current will flow. Now listen carefully and try to understand how this works as a full wave bridge rectifier. So before moving to next slide, I want you to focus on what you can see here. What are they? There is a AC supply, then you have a transformer, then there are four diodes connected in the form of a bridge, and the secondary windings of the transformer are connected to two ends of that bridge, and other two ends, a load resistance is connected. So is this diagram clear to you?
Yes.
Yes.
Okay. Now let us see how a full wave bridge rectifier works. So you need to draw these diodes. You will know how these diodes are to be drawn only once you learn how it works. So let us see the working principle of full wave bridge rectifier. So you have a bridge full wave rectifier here during positive half cycle. So we are going to see what happens when current flows in the positive half cycle. So this is the input voltage. Here you have the transformer. You have the four diodes here. So how the output we get. So during the positive half cycle, we know this end is positive and this end is negative. So current flows from positive to negative, right? So follow along this arrow mark. So from positive, we are starting to flow. The current will come here, and at this junction, it will see two diodes, D1 and D3. So through which of them it can flow? Will it go through D1 or will it go through D3?
D1.
D1, because the current want to go like this, and D1 is in the direction of the arrow mark and D3 is not in the direction. So when you go like this, it cannot go through D3. It will go through D1 when it reaches here. It reached the junction here. Now, there are two paths for it, either through the load resistance or through D4, through which the current will flow. Will it flow through the load resistance or through D4?
The load resistance.
Yeah, again, it cannot flow through D4 because it is coming in a direction opposite to the arrow mark. So it will go through the load resistance and reach this junction. Now, it has only one path, right? It came like this, so it will go through D2. And D2 is in the direction of the arrow mark is in the direction of the current flow. So it go through D2 and it will reach here and it will complete the cycle, complete the circuit. So is that clear how the current will flow? The current will flow first through D1 because D1 is forward bias and D3 is reverse. So it will flow through D1, then it will go through load resistance, then it will go through D2 and it will complete the circuit. So D1 will be in forward bias, D2 will be in forward bias, and in this path, it will offer a closed circuit for the forward bias. It cannot go through D3 and D4 because both D3 and D4 are reverse bias. So they will not provide a closed circuit path. They will provide only an open circuit path. So which means it cannot flow. So is that clear? How in a bridge rectifier during the positive half cycle, the current will flow. Is that clear to you?
Yes.
Okay. Now, let us see how in a negative half cycle, the current will flow. Let us see in the negative half cycle down here. Okay. During the negative half cycle, we have the upper part negative, lower part positive. Just the reverse of what we considered in the positive half cycle. Now follow along me. So always current flows from the positive to negative, right? So I'm going from here now, from the positive to negative. So along positive, the current comes here, reaches here, this junction. So which path will the current take? D4 or D2?
D4.
D4. Why? Now D4 is forward and D2 is reverse. So it will go through D4 and reaches the junction here. Now which path will it take? The load resistance RL or D1?
Load resistance.
Yeah, it will go through the load resistance, which means it will come in this way. So it will go through the load resistance because it cannot go through D1. D1 is reverse bias. So it will go through load resistance RL and it have reached this point. Now, there is only one way, that is D3. Can it flow through D3?
Yes.
Yes, because it's going in the direction of the arrow mark. It is forward bias. So it will go through D3 and come back to here, which means it will have a close path during the negative half cycle. But this time it will go through D4, load resistance, D3 and complete the circuit. Because here D4 and D3 are forward bias when it flow in this direction. And they offer a closed circuit path. While D1 and D2 are reverse bias and they will not offer a closed circuit path, it will be an open circuit. No current will flow through that. Now, the point to be noted here is in both these ways, see, when the current is passing from passing in the forward, positive half cycle and negative cycle, it is always going through the load resistance in the same direction. For me, it is from right to left. Here again, from right to left. So through the load resistance in both positive and negative half cycle, they are going in the same direction. So if you are the load resistance, then when you look at the current, it's always going from right to left in the same direction. So the load resistance will see that the current is going in the same direction. So the output, which is seen in the load resistance, the output is the load resistance. So we see that in the output, the current is always going in the same direction. Both the positive half cycle and the negative half cycle is coming in the same direction. So this is how it will go. So just to repeat this idea of working, I will show the same working with the full diagram for a full wave bridge rectifier. So here, without that support of the diagram, you will tell me what happens in the positive half cycle and negative half cycle. So during the positive half cycle, upper part is positive, lower part is negative. So here, the current comes like this, positive half cycle. So through which will it go now? It have reached here.
D1.
D1.
D1. Yes. So it will go through D1. Now it reached M. through which it will go?
Load resistance.
Yes, from M it will go to load resistance through ML, and at L, where will it go?
D3.
D3. So it will go to D3. Can it go? Okay, it will go to D3 and it will just complete the cycle because it doesn't want to go again. So here there is a negative terminal. So the current will go directly. So during the positive half cycle, it will go through D1, RL, D3. The circuit is complete. So the positive half cycle current went through M to L. So we got the positive half cycle. Now coming to negative half cycle, the current direction is reverse. So up I have negative, down I have positive. Okay. So now I'm starting from this point B because this is positive now. So I'm coming from here, it reach here. Through which diode will it go now?
D2.
D2. So it will go through D2, reached M. Where will it go? Through D1 or RL?
RL.
RL, because D1 is reverse now. So it will go through RL, and now where it have to complete the circuit. So it will go through D4 and complete the circuit. So from B, it can reach A. Its aim from B is to reach A, right? This is positive, this is negative. So when it start from here, it want to go through this mesh or the bridge and reach A. So it will come here, it go through D2, ML again, and D4 and get back. So in both the half cycle, it went from ML. So in the same direction. So the output voltage we will get in the same direction from M to L. So the negative half cycle also will appear in the same direction. Is that clear to you? How the full wave bridge rectifier works?
Yes.
Okay, so for a full wave bridge rectifier, you need to learn how to draw this diagram and how to draw the input and output. Okay, and maybe for the working principle, if you are asked, you may just tell that during the forward bias, during the positive half cycle, diode D1 and D3 are forward bias. So it will pass through them and it will pass from M to L through the load resistance. D4 and D2 will be reverse bias. And during the negative half cycle, what happens is diode D2 and D4 will be forward bias and it will again pass through ML, while D1 and D3 are reverse bias. So when you go through that, when you try to draw the circuit, just consider a positive half cycle and draw the diode here. So draw the other diode in the reverse way. And again, when you come through ML, draw the diode as forward. So once you draw these two, you can then consider the negative and draw the polarity of the diodes properly. Okay, so learn how to draw this diagram. You may not, you need not draw that the other two, which is more complex. Without this pink line, maybe you can draw. Okay, so it's not required. This is just to explain how it happens. So it is enough that you learn this thoroughly and through words explain the working. So that's all I wanted to teach you today.